Today on Little Experiments, you and I are going to play a game show together. Now this particular game is quite infamous in the mathematical world, and its solution has been a hot topic ever since the game came out. We're going to look at the Monty Hall Problem today. The original game goes like this. Imagine that this red poker chip is $1 million, and it's going to be under one of these three cups. Your job is to choose which cup it's under. But there's a twist. After your initial selection, I'll flip over a different cup and show you nothing under it, and give you the chance to switch to a different cup. At that point, you have another decision to make. Do you stick with your original choice, or do you select the other cup? Okay, let's play together. We'll use this dice to select which cup the prize is under, then we'll also use a second roll to indicate your choice. Now that we know where the actual prize is, and you've made your initial selection, here comes that wrinkle. As the game show host, I know nothing's under this cup, so I show it to you. And now you have to make a choice. Do you stick with your original guess, or do you switch to the remaining cup? Before moving on to the rest of the video, put a prediction in the comments below and see if you get it right at the end. We'll play 10 trials at a time, first with staying, and the second time with switching. We'll make our cup choice and winning cup using a random dice roller from random.org. Because we have 4 cups, we'll skip any roll of 5 or 6. The first 10 valid rolls will be our initial selection, and the second 10 valid rolls will be the cup with the chip. The silver chip is the winning chip, and the blue chip is our initial choice. In this first game, we'll stick with our original choice. Now we play again, except on this one, we'll switch to a different cup. For the switching case, we'll use our single die roll per trial to decide which cup to switch to. Odd numbers move up 1 and even numbers move up 2. Past the orange bar, I switched the gray chips on accident. Whoops, but I've corrected them here. Here are experiment 1 results. And after these 20 trials, it's not looking good for switching. Now we tap the power of Monte Carlo simulation. If you need a quick refresher, check out my video on random stocks versus the stock market. As the trials build up, it's becoming clear that switching is the superior strategy. It's like David Morin from Harvard says, why argue about it if we can simulate it? You can see there's a 25% chance if you stay, and about a 38% chance if you switch. Pretty cool, right? Okay, prepare yourself. We're going to do a little bit of math, but I'll walk you through it. We'll use a version of Bayes' theorem that is diachronic, or changing with events in time. In this form, our hypothesis represents the assertion of the winning cup number, and our data is which cup the host flips over, always revealing nothing under that particular cup. Let's assume we chose cup 3 initially, and then the host flips over cup 4, showing us nothing under it. Initially, each cup has the same chance of being the winning cup, so 1 out of 4. For the next calculation, let's start with cup 4, the one we are shown nothing is under. It is impossible for this cup to be the winning cup by the assumption that it is the one shown not to be the winning cup, so the probability is 0. Cup 3 is our initial choice, and if it is the winning cup, the host can show us any of the other 3 cups. Assuming that the choice is random, cup 4 being flipped over has a 1 in 3 chance. If cup 2 is the winning cup, and we choose cup 3 initially, this leaves cup 1 and cup 4 to be flipped, so cup 4 has a 1 in 2 chance. And the same is true for cup 1 as is true for cup 2. Alright, multiplying column 2 and column 3 together gives column 4. Nice, you've made it through the hard part. The last bit we need is the denominator from Bayes' theorem. We simply look this formula up and plug and chug with the values from our table we've already calculated. To get the final column, we simply divide the 4th column by that 1/3 value. And would you look at that? These numbers match our Monte Carlo simulation numbers pretty closely. So we've just shown 2 things. One, that our theoretical calculations match our Monte Carlo calculations, and 2, that switching is the superior strategy. Okay, alright. For the sake of completeness, we'll show the Monte Carlo solution to the standard problem.
And there we have it, the Monty Hall problem explained, both with demonstration and with Bayes' theorem from probability theory. Hope you enjoyed the video, and we'll see you on the next one.